All right, so last part for today. Two pieces. One, I want to just quickly talk about how we can go from equijoints to more complicated joints like inequalities, theta joints in general, and then conclude. Right, so we have these two components here. Now, first, just a very quick introduction. Why do we need actually inequality conditions? So here's a simple example from a social network analysis. We have, for instance, different discussion groups on Reddit. And there's one that say it's about conspiracy, another one documentaries. And so here, for instance, we can look at each of these articles as a tuple, like a database tuple with its metadata. For instance, this article above here, it has information about where is it posted, like this is the C2 here. Also, what kind of article is it referencing to, in which community was that posted, which is the C3. And there's other information like the timestamp, when it was posted, some sentiment measure, is it positive, is it negative in tone, a readability score, and so on. So now, what can we do with an interesting query here in this context? We can now look at finding path. For instance, in this case, can we find two articles, one referencing another and that one another? And so actually in this case, it doesn't have to be a specific article referencing another article. It could also be just an article referencing something in the community. And so we have a join where we're looking at matching community endpoints. And also we have conditions like a sequence of articles should have increasing timestamps. And maybe we're also looking for something like maybe a more negative sentiment sequence. So maybe the first article is negative on the second one on the third is even more negative, right? So something where, let's say, a community, some people make fun about other people being conspiracy theorists and so on. So in the end, we can then look at the sequence of articles and, for instance, look at those sequences that are more readable than others. And those could be something that somebody could study, for instance, in the context of sociology. This kind of analysis written as an SQL query looks like this. We have select some attributes we care about. We have the weight is just the sum of readability scores of the two articles that we're looking at. We're ordering by that weight. We're looking at the top 1000. And the join is between Reddit articles where we have a match on source of one versus target of the other. We have the increasing timestamps and also the decreasing sentiment, meaning a more negative sentiment in one than the other article. So there's a mix of inequality and equality conditions in this case. When we run this in a typical database, it essentially uses the naive query plan of computing the join first, which is of order n squared size, and then sorts the results. Now, using the factorization techniques that we're talking about here, we can actually get the top k results, let's say the top 1000, in essentially time that's linear in the input and linear in that number of results that we're looking at. And now here we're ignoring log factors, and that's actually not a big deal in this case because the log is actually essentially a log squared for this specific query, and so it doesn't have a strong impact beyond the linear complexity anyway. Quick reminder, since it's already a while ago, so we have a database setting again with multiple relations. Here we're joining L relations. Each of them has order n tuples in it. The assumptions are we're looking at data complexity, so the number of relations that we're joining is a constant. Similarly, the number of attributes in the relation is considered a constant because they don't typically grow, right? The schema is given, but the data keeps growing as people are writing articles. Any kind of index that we would want would have to be built on the fly. And we're looking here specifically at in-memory computation complexity. So here are the results. Some of them we've seen before. The lower bound for the time to the kth result, if we enumerate answers to such an inequality join, well, we cannot do better than n plus k. We have to look at the input, we have to produce the output. Now for equijoins, we saw before, just Nikos talked about it also, time to k is essentially linear for preprocessing plus k log k for the delay of outputting the results and of the join one by one. The naive join and rank approach, which is essentially what database optimizers pick typically, would be n to the power L plus k log n, which is much worse, clearly. And now the interesting part is that using these factorization techniques and just modifying them a little, and I'll tell you in a second how, we can actually guarantee, even for very complicated inequality joins, basically any disjunctive normal form of inequalities, that means we have conjunctions, disjunctions, equalities, inequalities all together in the joint condition, as long as it's acyclic, we can get in this case n times polylog n plus k log k. So that's not much more than the n plus k log k that we saw for the equijoins. So we just have this polylog penalty on the preprocessing time. And even for theta joins, we can actually get O of n squared plus k log k. So n squared, you may say, is a little big for large data, but it's much better than n to the power L. So how does it work? Just quick refresher, Nikos just talked about it. So essentially, we can look at this as a graph problem. Each of the tuples from the input relations like S, T, and R is a node in this graph. And then instead of equijoins, now we have these inequality conditions. So remember before when Nikos showed the equality, there are nodes in between that capture the common join attributes. So it's basically little fully connected graphs that are subgraphs that are connecting these neighboring layers together. Now, in general, if we have a theta join, the structure will look different. It's not just a simple equijoin structure, but we can capture that abstractly with what we call a tuple level factorization graph, or TLFG. And how does this graph look like? Essentially, what we have to make sure is, for correctness, it's a DAG that is between two neighboring layers. And there is a path from a tuple in one layer to a tuple in another, if and only if these two tuples are joining together. So for instance, s dot b less than t dot d. So if we're looking at the tuple like 1,2 here, it joins with 2,3. And so there should be a path between the two. On the other hand, from 1,2 to 1,1, since they're not joining, there should be no path. Now, out of all the possible ways to represent this property, right, to have a path, if and only if these tuples are joining, there are many different ways we can encode that. And they are actually impacting the running time of the algorithm in the end. So especially the size of that cloud here, of that graph, that determines the preprocessing time, right? The larger it is, the longer it takes to build it. On the other hand, the length of the longest path between any tuple here in one layer and the tuple in the next layer, that determines the delay. How long does it take me to enumerate these tuples and put them together to produce an output tuple? So what we want is basically these clouds to be small and also shallow, so that these paths are very short. So here's one way to do that. For instance, the most simple way to do that, the simplest way to do it would be directly connecting the joining tuples. That has definitely the property that two tuples are connected if and only if they're joining, right? We see here 1, 1, the b value is 1. It joins with all the tuples that have a greater value for d. So we have an arrow from 1, 1 to all the other tuples except for 1, 1, and so on for all the others. Now, not surprisingly, this has order n squared edges in general, right? So especially for an inequality condition, it will be actually something like n squared over 2. On the other hand, the depth is only 1. So we have a large graph, but it's very shallow. What does it give us now in terms of the cost of producing now, let's say, the top ranked tuple here using some enumeration algorithm like the ones that Nikos just talked about? Well, because of the graph size, it takes order n squared to build these little graphs between the layers. But then enumeration is fast, so it's just k log k delay for each of the output results. So this is not bad, but n squared is not really desirable. And the goal is basically to do better than that. And for inequalities, we can do better. So here's a way to construct it. We don't have a lot of time, so I'm not going to go into the details, but essentially the secret here is to use a structure where I think of V3 as essentially the median of the values of these two B and D sets of values. So if this is the median, we have all the smaller ones, it's about half of the data here, and all the larger ones, about half the data there. So a single node, similar to the equijoin, is now capturing essentially half of all these connections in a linear space. And then we can do the same recursively for each of the halves, left and right separately. And that gives us essentially an n log n size graph construction. Instead of depth 1, we now have depth 2. Every path needs 2 hops now to go through that intermediate node. And this is a construction for a single inequality like this. And for that, we get actually a time to k in the end when we enumerate on this graph, which is n log n because of the graph size, plus still k log k because of the constant length of these paths. This generalizes to multiple inequalities when we have a DNF of inequalities, and then this log just becomes a polylog. So this is a very elegant construction to do that. And so in general, what we do is we turn a join that has inequality conditions on relations of size n, order n, into an equijoin on relations of size n log n, in this case, or in general n polylog n, if there are multiple inequality conditions. And so this is actually feasible, considered tractable in practice, because it's not much more than linear time. And we can also generalize this factorization so that we can cover specific cases like band predicates in a better way than just using essentially a combination of inequalities, non-equality predicates, any kind of conjunctions and disjunctions of them. And we also have optimizations for improved memory consumption. Let me just show you very quickly some experimental results. So here we have our method that I just talked about, which is called factorized in this case. QuadEqui is a competitor that essentially uses the direct encoding, right? This is the order n squared encoding where we don't do anything clever about the graph between the layers. We just directly connect the tuples that are joining. And we're actually using an idealized version here for this competitor where we already have pre-materialized the results of that, construction of that graph. So the only time that's measured is basically after materialization. Similarly, there's a batch algorithm, which is essentially simulating what the database is doing, but it also gets already for free the time for the join. So essentially all it has to do is just do the right way of arranging and looking at those join results. So both of these are essentially idealized versions of real-world algorithms. And then we implemented the technique also to run, well, not our technique, we're running this as a SQL query in PSQL, which is Postgres, and SystemX, which is a commercial database. And here we're especially looking at a memory optimized execution. So to make it actually really as good as possible for relations that fit in memory. Also, I want to mention that in both cases we're using pre-built indexes. So this database really has the best possible way of implementing it, and we're leaving it up to the optimizer to pick the best possible plan. So first, here's an experiment with synthetic data. This is basically a graph example, right? So we have edges. So the schema is S from AI to AI plus 1. And then we're looking at a path. Like for instance here, select star, where we look at the sum of weights from these tuples from S1 and S2. And now instead of an equality, we have an inequality condition. So first, here's a graph that shows as we're increasing the input size of the relation. And notice that 2 to the power 14 is just something like 16,000. So these are pretty small relations, S, right, with 16,000 tuples. And we're looking at how long does it take to get a top 1,000 answers for a join of this kind of query. So both in the batch and the QuadEqui algorithm, they're pretty much the same thing here because we're only joining two relations. And so we can see here that as we're increasing input size, it goes from something like, less than a second to something like 10, 15 seconds. But beyond 16,000 input tuples, the algorithm basically runs out of memory. And the problem is it's trying to materialize the intermediate results, and it runs out of steam, out of memory pretty quickly. The databases actually do better because they can also use, disk if they have to. And you can see actually here, both of them behave very similar to the batch algorithm. And that actually also validates our implementation of the batch algorithm as a kind of idealized version of what the database engine would do. So here we see SystemX, the commercial database, is significantly better than Postgres, but still it kind of behaves like batch. It's just going further because it doesn't have this limit on memory. So it can actually page things out to disk if necessary. Our factorized method is actually a lot faster than all these techniques. So here, it's orders of magnitude difference in running time. And also it can easily handle a database that's 256 times larger than, for instance, the largest that this batch idealized algorithm could handle. So even though the output is actually very large for the full join, since we're only looking at the top 1,000 and our techniques can actually, through factorization, avoid computing the full output, it is much faster in practice also. And this is a Java implementation that, as we can see here, behaves also, this is a Java implementation, the batch algorithm behaves very similar to a really good commercial database system. Here's now the Reddit query, the same query I just talked about before, where we try to find, in this case, pairs of articles that are related to each other based on timestamps and sentiment. and also connect communities. Here we can see again batch. In this case, actually, we're changing now the number of relations that we're joining. So is it a path of 2 articles, 3, 4, or more articles? Batches here, it's equal to quad equi for this case. Quad equi then keeps going. Batch actually runs out of memory already for the 3-hop version of this query. The commercial database and PostgreSQL, they can handle a little larger than batch, but even they at some point really suffer from that explosion of intermediate results that they have to keep track of. And our factorized method actually does really well. It's a little slower than batch in the beginning, but it's the only one that actually keeps going and is orders of magnitude faster than this idealized quad equi algorithm. So these algorithms work, and they can handle predicates that are really difficult for databases in general, like inequalities. This is well known. These are not easy to handle, even if you just want to compute the output of a join query like that. And through factorization, we're able to get, for instance, the top 1,000 results in a time that's essentially like sorting the input, even if the actual output is orders of magnitude larger, like n to the power L. In the end, what we guarantee in general is that we have this time to k result, which is n times polylog n plus k log k. And we can apply that same idea also to other query types like unranked enumeration, aggregation, and we get then the analogous query time complexity guarantees. All right, so let's quickly conclude and see what we've talked about.
So, Mirek, we have like 1 minute to 11:30, so I don't know if there's a hard cutoff, so try to make it quick.
Yeah, I'm going to go quickly. So what did we discuss? We talked about conjunctive queries, which are essentially select from where join queries with end-connected constraints. We also explored extensions to union aggregation, for instance, through these DNFs of inequality join conditions, the order by clause. And we also looked at a variety of versions of that, where we looked at unranked enumeration, ranked enumeration, and also the notion of direct access. Can we jump to the median of a join output without actually even computing the full output? So we mentioned that briefly in the beginning. So in terms of the results that we have, in general, a query that joins L relations of size n each has complexity up to order n to the power L. Now the AGM bound can give us a tighter upper bound based on the specific properties of the query. For instance, we saw for the 3 cycle, it actually turns out to be n to the power 1.5 instead of the generic n to the power 3 upper bound there. The lower bound in general is omega n plus r, and it is actually achievable for acyclic queries when we use the Yanakakis algorithm that has these bottom up and top down sweeps, and then the join order has to follow that corresponding tree representation of the join. For cyclic queries in general, this kind of upper bound is not achievable, and so the best we can hope for is something like order n to the power d plus r, where d is a width parameter that depends on how far the cyclic query is away from a tree-shaped acyclic query. And these algorithms are using tree decompositions and also the worst-case optimal join algorithms to produce the nodes in these tree bags. Now, in order to make a database responsive, we need to do better than that, right? Something like n to the power L, even n to the power d plus k is not good enough if we just want a few results. And so what we have shown here is that by using clever techniques, even when the output is of size n to the power L, we can produce the first k results for unranked enumeration in time n plus k, which is linear in input and linear in k. For ranked enumeration, where we have a monotonic ranking function, we can do it in order n plus k log k, which is just slightly slower. And even for something more complicated like direct access, jumping to a specific position in the sorted output without producing that output, we can do that in n polylog n and k polylog k for certain class of acyclic queries and ranking functions. In general, also, when we try to go beyond the join itself, selections are easy to handle. Projections are surprisingly maybe hard. And the reason is essentially that projections are generating duplicates, right, by tuples that are distinct, becoming the same because of projecting away of certain columns. And that means delays between tuples become larger potentially. And that makes projections difficult. And so now it depends now what is projected, which attributes are projected out, and that determines if we can achieve something like n plus k or not in general for these kinds of queries in terms of TTK. Now, if we have non-equality conditions, we just talked about ranked enumeration, for instance, where we can have for any DNF of inequalities an n polylog n plus k log k delay until we get the top k results. And theta joins are a little slower with n squared plus k log k. So what is the secret sauce? And this is pretty much, concluding the discussion for today. There are essentially 5 important points. One is the semi-John reductions that came up everywhere. And as Wolfgang and also Nikos mentioned before, they get rediscovered because they're so important and so powerful. Dynamic programming played an important role, and then its generalization to compute the top 2 and top 3 and so on efficiently. Factorization we just talked about everywhere, and the secret is basically to find the best possible factorized representation so that, for instance, even a join that is order n squared size between 2 relations can be represented in linear space or maybe n polylog n space for inequality conditions. And then, as basically the enabler of factorization, we need semi-rings. And here I just have this as a little reminder. Essentially, instead of computing the long and tedious AC plus AD plus BC plus BD, we can use something more compact where we just add up these 2 and then multiply the corresponding sums. And this is really the power that makes factorization efficient in the end. What are the next steps? Well, we can look at more complicated predicates, something where we have, let's say, columns for multiple tables involved, more than 2. We can look at what happens when we have updates. How do we maintain these data structures efficiently? How can we do something like machine learning over factorized data? And so this is something that has been started to be explored. And the general question here is, what can we compute quickly or efficiently without having to materialize the entire John result? And that concludes our tutorial. Thank you very much.